Hello, and welcome to Calm Science Nights. I'm so glad you're here with me tonight. Before we begin our peaceful journey through the mystery of dark matter, if you find comfort in drifting off to the soothing rhythm of cosmic mysteries, please consider subscribing to the channel. It helps us create more of these tranquil explorations together. Now, settle into your most comfortable position. Let the weight of the day lift from your shoulders. Tonight, we're going to explore one of the universe's deepest mysteries, dark matter, the invisible substance that makes up most of the matter in the cosmos yet remains completely unseen. Over the next 100 facts, we'll trace humanity's journey from noticing something was wrong with the universe to realizing that most of what exists is hidden from our eyes, woven into the very fabric of space. There's no need to remember everything tonight. In fact, there's no need to stay awake at all. Let these words wash over you like gentle waves, each fact a soft ripple in the stream of discovery, carrying you peacefully towards sleep. Just allow the story to unfold at its own unhurried pace, the way the universe itself expands, slowly, gracefully, mysteriously, holding its secrets close. Close your eyes now, and imagine yourself floating in space, surrounded by darkness. Around you, you can see stars and galaxies glowing in the blackness, bright points of light scattered through the cosmic void. These are the things we can see, the ordinary matter made of atoms, the stuff of stars and planets in our own bodies. But between and around all this visible matter, invisible and undetectable except through its gravity, is something else. Something we call dark matter. And there is far more of it than everything we can see. Our story begins not with dark matter itself, but with a puzzle about the universe that astronomers noticed in the early 20th century. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying clusters of galaxies, vast collections of hundreds or thousands of galaxies bound together by gravity. Zwicky was particularly interested in the Coma cluster, a massive collection of galaxies about 320 million light-years from Earth. He was trying to measure the total mass of the cluster by observing how fast the galaxies within it were moving. The technique Zwicky used was based on a principle discovered by Newton centuries earlier: the stronger the gravitational pull holding a system together, the faster objects within that system must move to avoid falling inward. For a galaxy cluster, this means that if you measure how fast the galaxies are orbiting within the cluster, you can calculate how much total mass the cluster must contain to keep those galaxies from flying apart. It's a straightforward application of Newton's laws. Measure the speeds, calculate the mass needed to hold everything together. When Zwicky made his measurements in 1933, he found something deeply puzzling. The galaxies in the Coma cluster were moving extraordinarily fast, so fast that the cluster should have torn itself apart long ago. Based on the speeds he measured, Zwicky calculated that the cluster needed to be about 400 times more massive than the visible matter, all the stars and gas he could actually see, to provide enough gravitational pull to hold the galaxies together. There simply wasn't enough visible matter to account for the gravitational binding. Zwicky proposed a radical explanation. There must be some kind of invisible matter in the cluster that he couldn't detect with his telescopes but whose gravitational influence was holding everything together. He called this invisible substance Dunkle Materie, dark matter in German. The name was descriptive and somewhat poetic: matter that was dark, that didn't shine, that remained hidden from view yet exerted a powerful gravitational pull. It was a bold hypothesis, suggesting that most of the universe was made of something we couldn't see. But Zwicky's discovery was largely ignored or dismissed by the astronomical community for decades. The idea seemed too strange, too radical. Perhaps Zwicky had made an error in his calculations, astronomers thought. Perhaps there was some other explanation, dust or dim stars or some unknown astrophysical process that could account for the discrepancy. The notion that the universe was mostly made of invisible matter was simply too difficult to accept based on observations of a single galaxy cluster. The concept of dark matter might have faded into obscurity if not for the work of another astronomer several decades later. In the 1960s and 1970s, Vera Rubin, an American astronomer working at the Carnegie Institution, began making careful measurements of how galaxies rotate. Rubin was interested in spiral galaxies like our own Milky Way, beautiful disc-shaped collections of stars, gas, and dust rotating around a central bulge. She wanted to understand how these galaxies spun, how fast different parts moved, and what that motion could tell us about the distribution of mass within them. Rubin's approach was similar to Zwicky's in principle but applied to individual galaxies rather than galaxy clusters. She measured the rotation speeds of stars and gas at different distances from the centers of spiral galaxies. The expectation, based on how we understand gravity, was straightforward. Stars closer to the galaxy center should orbit faster than stars farther out, just as inner planets in our solar system orbit the sun faster than outer planets. Most of a galaxy's visible mass is concentrated in the bright central bulge and the dense inner disk, so the outer regions should have less gravitational pull and slower orbital speeds. But that's not what Rubin found. Using a spectrograph to measure the Doppler shifts of light from different parts of galaxies, she discovered that stars in the outer regions of spiral galaxies were moving just as fast as stars closer to the center, sometimes even faster. The rotation curves, as they're called, were flat rather than declining. This was completely unexpected and deeply puzzling. Based on the visible matter in these galaxies, the outer stars were moving far too fast. They should have been flung out into intergalactic space long ago by their own orbital speed. Rubin's observations, published in the 1970s and refined throughout the 1980s, confirmed and extended what Zwicky had found decades earlier but had been largely overlooked. Galaxy after galaxy showed the same pattern, flat rotation curves indicating that there was far more mass in these galaxies than could be accounted for by visible stars and gas. The only way to explain the observations was to assume that galaxies are embedded in enormous halos of invisible matter extending far beyond the visible disk, dark matter halos that contain most of the galaxy's mass. Unlike Zwicky's work, Rubin's findings could not be easily dismissed. She had measured dozens of galaxies with great precision, and the pattern was consistent and undeniable. Other astronomers repeated her observations and confirmed her results. The evidence was becoming overwhelming. Galaxies, and indeed the entire universe, contained vast amounts of matter that emitted no light, absorbed no light, and remained completely invisible except through its gravitational effects. The universe was not what it appeared to be. And so our journey has begun with the puzzle astronomers noticed in the early 20th century, starting with Fritz Zwicky studying galaxy clusters in the 1930s. We learned Zwicky was particularly interested in the Coma cluster, massive collection of galaxies about 320 million light-years from Earth, trying to measure the cluster's total mass by observing how fast galaxies within it were moving. We discovered the technique Zwicky used was based on principle discovered by Newton centuries earlier: stronger gravitational pull holding system together. Faster objects within that system must move to avoid falling inward. For galaxy cluster, this means if measure how fast galaxies orbiting within cluster can calculate how much total mass cluster must contain to keep those galaxies from flying apart. Straightforward application of Newton's laws. Measure speeds, calculate mass needed to hold everything together. We found when Zwicky made measurements in 1933 found something deeply puzzling: galaxies in Coma cluster moving extraordinarily fast, so fast cluster should have torn itself apart long ago. Based on speeds measured, Zwicky calculated cluster needed to be about 400 times more massive than visible matter, all stars and gas he could actually see, to provide enough gravitational pull to hold galaxies together, simply not enough visible matter to account for gravitational binding. We learned Zwicky proposed radical explanation: must be some kind of invisible matter in cluster he couldn't detect with telescopes but whose gravitational influence holding everything together. Called this invisible substance Dunkel Materie, dark matter in German. Name was descriptive and somewhat poetic: matter that was dark, didn't shine, remained hidden from view yet exerted powerful gravitational pull. Bold hypothesis suggesting most universe made of something we couldn't see. We discovered Zwicky's discovery largely ignored or dismissed by astronomical community for decades. Idea seemed too strange, too radical. Perhaps Zwicky made error in calculations, astronomers thought. Perhaps some other explanation, dust or dim stars or unknown astrophysical process, could account for discrepancy. Notion that universe mostly made of invisible matter simply too difficult to accept based on single galaxy cluster observations. We found dark matter concept might have faded into obscurity if not for another astronomer's work several decades later. In 1960s to 1970s, Vera Rubin, American astronomer working at Carnegie Institution, began making careful measurements of how galaxies rotate. Rubin interested in spiral galaxies like our Milky Way, beautiful disc-shaped star, gas, dust collections rotating around central bulge, wanted to understand how these galaxies spun, how fast different parts moved, what that motion could tell about mass distribution within them. We learned Rubin's approach similar to Zwicky's in principle but applied to individual galaxies rather than galaxy clusters, measured rotation speeds of stars and gas at different distances from galaxy centers. Expectation based on gravity understanding was straightforward. Stars closer to galaxy center should orbit faster than stars farther out, just as inner planets in solar system orbit sun faster than outer planets. Most galaxies' visible mass concentrated in bright central bulge and dense inner disk, so outer regions should have less gravitational pull and slower orbital speeds. We discovered, but that's not what Rubin found. Using spectrograph to measure Doppler shifts of light from different galaxy parts, discovered stars in spiral galaxy outer regions moving just as fast as stars closer to center, sometimes even faster. Rotation curves, as they're called, were flat rather than declining, completely unexpected and deeply puzzling. Based on visible matter in these galaxies, outer stars moving far too fast should have been flung out into intergalactic space long ago by own orbital speed. We found Rubin's observations published in 1970s and refined throughout 1980s confirmed and extended what Zwicky found decades earlier but had been largely overlooked. Galaxy after galaxy showed same pattern. flat rotation curves indicating far more mass in galaxies than could be accounted for by visible stars and gas. Only way to explain observations was assume galaxies embedded in enormous invisible matter halos extending far beyond visible disk, dark matter halos containing most galaxies' mass. We learned unlike Zwicky's work, Rubin's findings could not be easily dismissed, had measured dozens of galaxies with great precision, pattern consistent and undeniable. Other astronomers repeated observations confirming results, evidence becoming overwhelming. Galaxies and indeed entire universe contained vast amounts of matter emitting no light, absorbing no light, remaining completely invisible except through gravitational effects. Universe was not what it appeared to be. Each fact a gentle step in understanding slow emergence, the gradual realization that something invisible and mysterious pervades the universe. From Zwicky's galaxy clusters to Rubin's rotation curves, from ignored hypothesis to undeniable evidence, the story of discovering that most of what exists cannot be seen. Feel yourself in that gradual awakening now, standing with those astronomers measuring galaxy speeds, calculating masses, realizing the numbers don't add up. Something is missing, something vast and invisible, holding galaxies together with its gravity. There's nothing to solve tonight, nothing to grasp. Just rest in the gentle mystery of the invisible universe, in the peaceful recognition that most of reality is hidden from our eyes, yet reveals itself through its gravitational embrace. Let the dark matter carry you now, that invisible substance surrounding every galaxy, holding the cosmos together, unseen but present, mysterious and patient, drifting gently towards sleep. As we continue our peaceful journey through the story of dark matter, we move from the initial observations that something was missing in the universe to the growing realization of just how much dark matter there must be and what it might, or might not, be made of. The evidence from galaxy rotation curves was compelling, but scientists needed to understand what this mysterious substance could possibly be. The search for answers would lead to some of the most creative and imaginative thinking in the history of astronomy. Once astronomers accepted that Vera Rubin's observations were real and that galaxies truly did contain far more mass than could be seen, the obvious question became, what is this dark matter made of? The first natural assumption was that dark matter might simply be ordinary matter, the same atoms that make up stars and planets in our own bodies, that just happen to not be shining. After all, not all matter in the universe emits light. There could be many objects made of normal atomic matter that would be invisible or very dim. Astronomers began considering various candidates for what they called MACHOs, an acronym for massive compact halo objects. These would be objects made of ordinary matter but too dim to see easily, brown dwarfs, failed stars that never got hot enough to ignite nuclear fusion, white dwarfs, the cooling remnants of dead stars, neutron stars, black holes, or even very faint red dwarf stars. Perhaps the dark matter halos around galaxies were simply filled with countless billions of these dim objects, their combined mass accounting for the missing matter. This was an appealing idea because it didn't require any new physics, just lots of objects we already knew existed but couldn't easily detect. In the 1990s, astronomers conducted extensive searches for MACHOs using a clever technique called gravitational microlensing. When a massive object passes in front of a distant star, its gravity bends the starlight, temporarily making the star appear brighter. By monitoring millions of stars and looking for these brief brightening events, astronomers hoped to detect the machos passing in front of them. The microlensing surveys did detect some machos. There were indeed some dark, compact objects lurking in the galactic halo. But when astronomers tallied up all the detections and estimated how many machos there must be, they found that these objects could account for only a small fraction of the dark matter, perhaps 20% at most. The vast majority of the missing mass couldn't be explained by brown dwarfs, white dwarfs, or any other form of ordinary matter that simply wasn't shining. Dark matter had to be something else, something more exotic. Another line of evidence pointing away from ordinary matter came from cosmology, the study of the universe's origin and evolution. In the first few minutes after the Big Bang, when the universe was extremely hot and dense, nuclear reactions created the lightest elements, hydrogen, helium, and trace amounts of lithium. The relative abundances of these elements depend sensitively on how much ordinary matter, protons and neutrons, was present in the early universe. By measuring these abundances today and running the nuclear physics calculations backward, cosmologists could determine how much ordinary matter the universe contains. The answer from this Big Bang nucleosynthesis calculation was clear and precise. Ordinary matter, everything made of protons, neutrons, and electrons, makes up only about 5% of the total mass energy of the universe. This was far too little to account for the dark matter inferred from galaxy rotation curves and galaxy cluster dynamics. The dark matter, whatever it was, couldn't be made of ordinary atoms. It had to be something fundamentally different, some kind of matter that didn't participate in nuclear reactions during the Big Bang, that didn't emit or absorb light, and that interacted with ordinary matter only through gravity. Particle physicists had a candidate ready: WIMPs, or weakly interacting massive particles. These hypothetical particles would have been created in the early universe, shortly after the Big Bang, and would have survived to the present day. Unlike ordinary matter particles, WIMPs would interact only through gravity and possibly through the weak nuclear force, one of the four fundamental forces of nature, responsible for certain types of radioactive decay. This weak interaction would make WIMPs extraordinarily difficult to detect, but not quite impossible. The WIMP hypothesis was particularly appealing because it emerged naturally from theories physicists had developed for other reasons, extensions to the standard model of particle physics called supersymmetry. These theories predicted the existence of new heavy particles with exactly the properties needed to be dark matter. If WIMPs made up the dark matter, countless billions of them would be passing through Earth, through your body, every second, interacting so rarely with ordinary matter that they would ghost through as if we weren't there. Only occasionally, perhaps once in a trillion interactions, would a WIMP collide with an atomic nucleus in a way we might detect. Starting in the 1980s and continuing to the present day, physicists have built increasingly sensitive detectors deep underground, shielded from cosmic rays and other background radiation, hoping to catch one of these rare WIMP collisions. Experiments like CDMS, Xenon, LUX, and dozens of others have searched for the telltale sign of a WIMP bumping into a nucleus. The detectors have become extraordinarily sensitive, capable of detecting energy depositions as small as a few particles of light or the tiny vibration of a crystal lattice disturbed by a collision. But despite decades of searching with ever more sensitive instruments, no definitive WIMP signal has been found. The detectors have ruled out many of the predicted WIMP properties. If WIMPs exist, They must be even more weakly interacting or have different masses than the simplest theories suggested. This null result doesn't mean WIMPs don't exist, but it has led physicists to consider other possibilities. Perhaps dark matter is something even more exotic than WIMPs, or perhaps it consists of multiple different types of particles, or perhaps our understanding of gravity itself needs modification. And so we learned once astronomers accepted Vera Rubin's observations were real and galaxies truly contain far more mass than could be seen. Obvious question became, what is this dark matter made of? First natural assumption was dark matter might simply be ordinary matter, same atoms making up stars and planets in our bodies, that just happen to not be shining. After all, not all universe matter emits light. Could be many objects made of normal atomic matter that would be invisible or very dim. We discovered astronomers began considering various candidates for what they called MACHOs, massive compact halo objects acronym, objects made of ordinary matter but too dim to see easily, brown dwarfs, failed stars never getting hot enough to ignite nuclear fusion, white dwarfs, cooling dead star remnants, neutron stars, black holes, or even very faint red dwarf stars. Perhaps dark matter halos around galaxies simply filled with countless billions of these dim objects, their combined mass accounting for missing matter. We found this appealing idea because it didn't require any new physics, just lots of objects we already knew existed but couldn't easily detect. In 1990s, astronomers conducted extensive MACHO searches using clever technique called gravitational microlensing. When massive object passes in front of distant star, its gravity bends starlight, temporarily making star appear brighter. By monitoring millions of stars looking for these brief brightening events, astronomers hoped to detect MACHOs passing in front of them. We learned microlensing surveys did detect some MACHOs, indeed some dark compact objects lurking in galactic halo, but when astronomers tallied all detections and estimated how many MACHOs there must be found, these objects could account for only small dark matter fraction, perhaps 20% at most. Vast majority of missing mass couldn't be explained by brown dwarfs, white dwarfs, or any other ordinary matter form simply not shining. Dark matter had to be something else, something more exotic. We discovered another line of evidence pointing away from ordinary matter came from cosmology, study of universe's origin and evolution. In first few minutes after Big Bang, when universe extremely hot and dense, nuclear reactions created lightest elements, hydrogen, helium, and trace lithium amounts. Relative abundances of these elements depend sensitively on how much ordinary matter, protons and neutrons, was present in early universe. By measuring these abundances today and running nuclear physics calculations backward, cosmologists could determine how much ordinary matter universe contains. We found answer from Big Bang nucleosynthesis calculation was clear and precise. Ordinary matter, everything made of protons, neutrons, electrons, makes up only about 5% of total universe mass energy, far too little to account for dark matter inferred from galaxy rotation curves and galaxy cluster dynamics. Dark matter, whatever it was, couldn't be made of ordinary atoms. Had to be something fundamentally different, some matter kind not participating in nuclear reactions during Big Bang, not emitting or absorbing light, interacting with ordinary matter only through gravity. We learned particle physicists had candidate ready, WIMPs, weakly interacting massive particles, hypothetical particles created in early universe shortly after Big Bang, surviving to present day. Unlike ordinary matter particles, WIMPs would interact only through gravity and possibly through weak nuclear force, one of four fundamental nature forces responsible for certain radioactive decay types. Weak interaction would make WIMPs extraordinarily difficult to detect but not quite impossible. We discovered WIMP hypothesis particularly appealing because emerged naturally from theories physicists developed for other reasons, standard model of particle physics extensions called supersymmetry. Theories predicted existence of new heavy particles with exactly properties needed to be dark matter. If WIMPs made up dark matter, countless billions would be passing through Earth, through your body every second, interacting so rarely with ordinary matter would ghost through as if we weren't there, only occasionally, perhaps once in trillion interactions, would WIMP collide with atomic nucleus in way we might detect. We found starting 1980s continuing to present-day physicists built increasingly sensitive detectors deep underground, shielded from cosmic rays and other background radiation, hoping to catch one of these rare WIMP collisions. Experiments like CDMS, Xenon, LUX, and dozens of others searched for telltale WIMP bumps into nucleus sign. Detectors became extraordinarily sensitive, capable of detecting energy depositions as small as few light particles or tiny crystal lattice vibration disturbed by collision. We learned, but despite decades of searching with ever more sensitive instruments, no definitive WIMP signal found. Detectors ruled out many predicted WIMP properties. If WIMPs exist, must be even more weakly interacting or have different masses than simplest theories suggested. Null result doesn't mean WIMPs don't exist, but led physicists to consider other possibilities. Perhaps dark matter, something even more exotic than WIMPs, perhaps consists of multiple different particle types. Perhaps our gravity understanding itself needs modification. Each fact a gentle step in understanding's deepening, the gradual realization that dark matter is not simply matter that doesn't shine, but something truly exotic and strange. From machos to microlensing, from Big Bang nucleosynthesis to WIMPs, from underground detectors to null results, the search for what dark matter is made of continues. Rest in this ongoing mystery now. This recognition that despite decades of searching we still don't know what dark matter is. The universe holds its secrets close, revealing itself only slowly, particle by particle, observation by observation. Let yourself drift with these invisible particles, these WIMPs perhaps streaming through you this very moment, interacting so weakly you could never feel them, ghosting through your body and through Earth itself, peaceful and undetectable, carried gently towards sleep. As we continue our peaceful journey through the story of dark matter, we move from the search for what dark matter might be made of to exploring the overwhelming evidence that it exists throughout the universe. While we still don't know what dark matter is, astronomers have found its gravitational fingerprints everywhere they look, in the largest structures in the cosmos and in the subtle patterns of light left over from the Big Bang itself. The invisible universe reveals itself through gravity alone. One of the most dramatic and visually striking pieces of evidence for dark matter comes from observations of colliding galaxy clusters. When two massive clusters of galaxies collide, a slow-motion cosmic crash taking millions of years, the collision separates the different components of matter in a way that reveals dark matter's presence. The collision of a pair of galaxy clusters called the Bullet Cluster, studied extensively in the early 2000s, provided perhaps the most direct evidence for dark matter that astronomers had ever seen. When the two clusters that form the Bullet Cluster passed through each other, the ordinary matter behaved differently from the dark matter. The hot gas between the galaxies, ordinary matter heated to millions of degrees and glowing in X-rays, collided and slowed down, creating friction and shock waves. This gas makes up most of the ordinary matter in galaxy clusters, far more than the stars themselves. Astronomers could see this hot gas using X-ray telescopes, and it was concentrated in the center where the two clusters had collided. But when astronomers measured where most of the mass in the system was located using gravitational lensing, the bending of light from distant galaxies by the cluster's gravity, they found something remarkable. The center of mass wasn't where the hot gas was. Instead, it was in two separate regions on either side of the collision, exactly where the galaxies themselves had passed through. The dark matter, which makes up most of the mass, had passed right through the collision like ghosts, unaffected by the crash because dark matter doesn't interact electromagnetically. It doesn't collide or create friction, it just drifts through, responding only to gravity. This clean separation of ordinary matter and dark matter in the bullet cluster was powerful evidence that dark matter couldn't simply be a modification of our understanding of gravity. If there were no dark matter and gravity just worked differently than we thought, the mass and the ordinary matter should be in the same place. But they weren't. The mass, measured through gravitational lensing, was clearly separate from the ordinary matter, seen glowing in X-rays. Something invisible and massive had passed through the collision, and that something could only be dark matter. Beyond individual clusters, dark matter's influence appears in the largest structures in the universe. When astronomers map the positions of millions of galaxies across vast volumes of space, they find that galaxies aren't distributed randomly. Instead, they're arranged in an enormous cosmic web, long filaments and sheets of galaxies surrounding vast empty voids. This cosmic web structure, stretching across hundreds of millions of light years, is one of the most striking patterns in the universe. Computer simulations of how the universe evolves under gravity reveal that this cosmic web structure is a natural consequence of dark matter. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly with only tiny density variations, slight ripples in the distribution of matter. But over billions of years, gravity amplified these small variations. Regions that were slightly denser attracted more matter, becoming denser still. Dark matter, which feels only gravity and isn't affected by pressure or radiation, clumped together first, creating the gravitational scaffolding along which ordinary matter could flow. The simulations show that dark matter forms a vast network of filaments connecting massive nodes where galaxy clusters form. Ordinary matter, following the gravitational pull of dark matter, falls into these same structures, creating the cosmic web of galaxies we observe. Without dark matter, the simulations don't produce structures that match what we see. There wouldn't have been enough time since the Big Bang for gravity acting on ordinary matter alone to create the elaborate cosmic web that exists today. Dark matter was essential for building the large-scale structure of the universe. Perhaps the most profound evidence for dark matter comes from the cosmic microwave background, the faint afterglow of the Big Bang itself. This radiation, discovered accidentally in 1964 by Arno Penzias and Robert Wilson, fills the entire universe. It's the cooled-down remnant of the intense heat from the early universe, now appearing as microwave radiation with a temperature just 2.7 degrees above absolute zero. This ancient light has been traveling through space for nearly 13.8 billion years, carrying information about the universe as it was just 380,000 years after the Big Bang. When astronomers map the cosmic microwave background with high precision, as satellites like COBE, WMAP, and Planck have done, they find it's not perfectly uniform. There are tiny temperature variations, typically only about 1 part in 100,000, creating a mottled pattern across the sky. These temperature fluctuations correspond to density variations in the early universe, regions that were slightly hotter or cooler, slightly denser or less dense. These were the seeds from which all cosmic structure grew. The pattern of these fluctuations contains an enormous amount of information about the universe's composition and history. By analyzing the sizes and amplitudes of the hot and cold spots, cosmologists can determine how much ordinary matter, dark matter, and dark energy the universe contains, how old the universe is, how fast it's expanding, and many other fundamental parameters. It's like cosmic archaeology, reading the history of the universe from subtle patterns in ancient light. The cosmic microwave background data reveals that the universe is approximately 68% dark energy, 27% dark matter, and only 5% ordinary matter, everything made of atoms, all the stars and planets and gas and dust we can see. Dark matter outweighs ordinary matter by more than 5 to 1. The precision of these measurements is remarkable, determined to better than 1% accuracy. The patterns in the cosmic microwave background wouldn't make sense without dark matter, the acoustic oscillations, the pattern of peaks and valleys in the fluctuation spectrum, all depend critically on dark matter being present in these proportions. And so we learned one of most dramatic and visually striking dark matter evidence pieces comes from colliding galaxy cluster observations. When two massive clusters collide, slow-motion cosmic crash taking millions of years, collision separates different matter components revealing dark matter's presence. Bullet cluster collision, pair of galaxy clusters studied extensively early 2000s, provided perhaps most direct dark matter evidence astronomers ever seen. We discovered when two bullet cluster-forming clusters passed through each other, ordinary matter behaved differently from dark matter, hot gas between galaxies, ordinary matter heated to millions of degrees glowing in X-rays, collided and slowed down, creating friction and shock waves. This gas makes up most galaxy cluster ordinary matter, far more than stars themselves. Astronomers could see hot gas using X-ray telescopes, concentrated in center where two clusters collided. We found but when astronomers measured where most system mass was located using gravitational lensing, light bending from distant galaxies by clusters' gravity, found something remarkable. Mass center wasn't where hot gas was, instead in two separate regions on either collision side, exactly where galaxies themselves had passed through. Dark matter, making up most mass, passed right through collision like ghosts, unaffected by crash because dark matter doesn't interact electromagnetically, doesn't collide or create friction, just drifts through, responding only to gravity. We learned this clean bullet cluster ordinary matter and dark matter separation was powerful evidence dark matter couldn't simply be gravity understanding modification. If no dark matter and gravity just worked differently than thought, mass and ordinary matter should be in same place, but weren't. Mass, measured through gravitational lensing, clearly separate from ordinary matter, seen glowing in X-rays. Something invisible and massive passed through collision. That something could only be dark matter. We discovered beyond individual clusters dark matter's influence appears in universe's largest structures. When astronomers map millions of galaxy positions across vast space volumes, find galaxies aren't randomly distributed. instead arranged in enormous cosmic web, long filaments in sheets of galaxies surrounding vast empty voids. Cosmic web structure stretching across hundreds of millions of light-years is one of the universe's most striking patterns. We found computer simulations of how universe evolves under gravity reveal cosmic web structure as natural dark matter consequence. In early universe shortly after Big Bang, matter distributed almost uniformly with only tiny density variations, slight distribution ripples. But over billions of years, gravity amplified small variations. Regions slightly denser attracted more matter, becoming denser still. Dark matter, feeling only gravity, unaffected by pressure or radiation, clumped together first, creating gravitational scaffolding along which ordinary matter could flow. We learned simulations show dark matter forms vast filament network connecting massive nodes where galaxy clusters form. Ordinary matter following dark matter gravitational pull falls into same structures, creating observed galaxy cosmic web. Without dark matter, simulations don't produce structures matching what we see. Wouldn't have been enough time since Big Bang for gravity acting on ordinary matter alone to create today's existing elaborate cosmic web. Dark matter was essential for building universe's large-scale structure. We discovered perhaps most profound dark matter evidence comes from cosmic microwave background, faint Big Bang afterglow itself. Radiation discovered accidentally 1964 by Arno Penzias and Robert Wilson fills entire universe. Cooled down remnant of early universe intense heat now appearing as microwave radiation with temperature just 2.7 degrees above absolute zero. Ancient light traveling through space nearly 13.8 billion years, carrying information about universe as it was just 380,000 years after Big Bang. We found when astronomers map cosmic microwave background with high precision, satellites like COBE, WMAP, Planck, find it's not perfectly uniform. Tiny temperature variations, typically only about 1 part in 100,000, creating mild sky pattern. Temperature fluctuations correspond to early universe density variations, regions slightly hotter or cooler, slightly denser or less dense. These were seeds from which all cosmic structure grew. We learned fluctuation pattern contains enormous information about universe composition and history. By analyzing hot and cold spot sizes and amplitudes, cosmologists can determine how much ordinary matter, dark matter, and dark energy universe contains, how old universe is, how fast it's expanding, many other fundamental parameters. Like cosmic archaeology, reading universe history from subtle ancient light patterns. We discovered cosmic microwave background data reveals universe approximately 68% dark energy, 27% dark matter, only 5% ordinary matter, everything made of atoms, all stars and planets and gas and dust we can see. Dark matter outweighs ordinary matter by more than 5 to 1. Measurement precision remarkable, determined to better than 1% accuracy. Cosmic microwave background patterns wouldn't make sense without dark matter. Acoustic oscillations, fluctuation spectrum peaks and valleys pattern all depend critically on dark matter being present in these proportions. Each fact a gentle step in understanding's expansion, the gradual realization that dark matter's evidence is everywhere, in colliding clusters, in the cosmic web, in the ancient light of the Big Bang. From bullet clusters separated mass to cosmic web simulations, from cosmic microwave background fluctuations to universe composition ratios, all pointing to invisible matter pervading cosmos. Rest in this overwhelming evidence now. This recognition that dark matter is not speculation but well-established reality. The universe is mostly invisible, mostly made of something we cannot see, yet the evidence for its existence is undeniable. Let yourself drift with the cosmic web, those vast dark matter filaments connecting galaxy clusters across hundreds of millions of light years, the invisible scaffolding holding the universe together, ancient and patient, carried gently towards sleep. As we continue our peaceful journey through the story of dark matter, we move from the cosmic scale evidence to exploring alternative dark matter candidates and the subtle ways dark matter might reveal itself. While WIMPs have dominated the search for decades, physicists have imagined many other possibilities for what dark matter could be, some exotic, some elegant, all mysterious. The search continues in laboratories, in telescopes, and in the mathematical spaces of theoretical physics. One particularly intriguing dark matter candidate that has gained attention in recent years is the axion, a hypothetical particle much lighter than a WIMP, possibly billions of times lighter than an electron. Axions were originally proposed in the 1970s not to explain dark matter but to solve a completely different problem in particle physics called the strong CP problem. It was only later that physicists realized that if axions existed, they would have been produced in enormous quantities in the early universe and could naturally account for all the dark matter we observe. Unlike WIMPs, which would be relatively heavy and rare, axions would be extraordinarily light and abundant. If dark matter is made of axions, there might be trillions upon trillions of them passing through every cubic centimeter of space, including through your body, right now. They would form a vast invisible ocean permeating the galaxy, all the particles moving at roughly the same speed as they orbit the galactic center along with the visible stars and gas. This sea of axions wouldn't interact with ordinary matter through electromagnetic forces at all, but in strong magnetic fields, they could very rarely convert into photons, particles of light. Experiments designed to detect axions exploit this rare conversion. They use powerful magnets and ultra-sensitive detectors tuned to pick up the faint radio signals that would be produced if axions were converting to photons inside the magnetic field. These experiments have exotic names like ADMX, the Axion Dark Matter Experiment, and Haystack, and they search patiently for the whisper-quiet signal of dark matter revealing itself. So far, like the WIMP searches, axion experiments have found no definitive signal, but they continue to probe new regions of parameter space, narrowing down where axions might hide. Another possibility that physicists have considered is that dark matter might be made of primordial black holes formed not from the collapse of stars but in the very early universe, perhaps in the first second after the Big Bang. If conditions were right, regions of space that were slightly denser than average could have collapsed directly into black holes without ever forming stars first. These primordial black holes could have a wide range of masses, from as small as an asteroid to many times the mass of the Sun. Primordial black holes are appealing as a dark matter candidate because they would be made of ordinary space-time, just extremely warped. They wouldn't require any new particles or exotic physics, just the same general relativity we already understand. They would be completely dark, emitting no light, and would interact with other matter only through gravity, exactly as dark matter appears to do. For a while, this seemed like a promising possibility that could explain dark matter without invoking particle physics beyond the standard model. However, multiple lines of evidence have now ruled out primordial black holes as the primary component of dark matter, at least for most mass ranges. The gravitational microlensing surveys that searched for machos would have detected primordial black holes in certain mass ranges, and they didn't find enough of them. Observations of the cosmic microwave background constrain how many small primordial black holes could have formed. Ancient stars, which would have been disrupted by close encounters with black holes, survived in larger numbers than expected if primordial black holes were common. Each piece of evidence closed off another range of possible primordial black hole masses, leaving only narrow windows where they might still account for dark matter. Beyond specific particle candidates, physicists have also explored more radical possibilities. Some theories suggest that dark matter might not be particles at all but rather a modification to our understanding of gravity itself. The most developed of these ideas is called MOND, Modified Newtonian Dynamics, proposed by physicist Mordechai Milgram in 1983. MOND suggests that Newton's law of gravity needs to be modified when gravitational accelerations become extremely weak, as they are in the outer regions of galaxies. In MOND, the relationship between force and acceleration changes when accelerations fall below a certain threshold, roughly 1/10,000,000th of Earth's surface gravity. Below this threshold, gravitational effects become stronger than Newton's laws would predict, which could explain why stars in the outer parts of galaxies orbit faster than expected without needing to invoke dark matter. MOND has had some successes. It can explain galaxy rotation curves quite well with a single adjustable parameter, and it predicted a relationship between galaxy properties and rotation that was later observationally confirmed. However, MOND faces significant challenges. It struggles to explain the behavior of galaxy clusters like the Bullet cluster, where the separation of mass and ordinary matter seems to require actual dark matter rather than modified gravity. It doesn't naturally explain the patterns in the cosmic microwave background, which fits so well with dark matter models. And MOND is not a complete theory of gravity. It modifies Newtonian gravity but doesn't have a fully developed relativistic version that can replace Einstein's general relativity in all situations. Most physicists view MOND as an interesting idea that captures something true about galaxy dynamics but ultimately doesn't provide a complete alternative to dark matter. The ongoing failure to directly detect dark matter particles, whether WIMPs or axions or anything else, has led some physicists to wonder whether dark matter might be even more exotic than anyone has imagined. Perhaps dark matter exists in a dark sector, an entire hidden realm of particles and forces that mirrors our own but interacts with ordinary matter only through gravity. In this view, there might be dark photons, dark electrons, even dark atoms and dark chemistry, all invisible to us because they don't couple to the electromagnetic force that allows us to see things. In the most elaborate versions of this idea, there could be dark stars, dark planets, perhaps even dark life, an entire shadow universe coexisting with ours, overlapping in space but forever invisible because the two realms interact only gravitationally. We would feel the dark matter's gravity, and it would feel ours, but we could never see it, touch it, or communicate with it in any conventional way. This is highly speculative, of course, and there's no direct evidence for such elaborate dark sectors, but the idea illustrates how far physicists are willing to go in imagining what dark matter might be. And so we learned one particularly intriguing dark matter candidate gaining recent years' attention is axion, hypothetical particle much lighter than WIMP, possibly billions of times lighter than electron. Axions originally proposed 1970s not to explain dark matter but to solve completely different particle physics problem called strong CP problem. Only later physicists realized if axions existed would have been produced in enormous quantities in early universe and could naturally account for all observed dark matter. We discovered unlike WIMPs, relatively heavy and rare, axions would be extraordinarily light and abundant. If dark matter made of axions might be trillions upon trillions passing through every cubic centimeter of space, including through your body right now, would form vast invisible ocean permeating galaxy, all particles moving at roughly same speed as orbit galactic center along with visible stars and gas. Axions C wouldn't interact with ordinary matter through electromagnetic forces at all, but in strong magnetic fields could very rarely convert into photons, light particles. We found experiments designed to detect axions exploit this rare conversion, use powerful magnets and ultra-sensitive detectors tuned to pick up faint radio signals produced if axions converting to photons inside magnetic field. Experiments have exotic names like ADMX, Axion Dark Matter Experiment, and Haystack. Search patiently for whisper quiet dark matter revealing itself signal. So far, like WIMP searches, Axion experiments found no definitive signal but continue probing new parameter space regions, narrowing down where axions might hide. We learned another possibility physicists considered as dark matter might be made of primordial black holes. Black holes formed not from star collapse but in very early universe, perhaps first second after Big Bang. If conditions right, regions of space slightly denser than average could have collapsed directly into black holes without ever forming stars first. Primordial black holes could have wide mass range from as small as asteroid to many times sun's mass. We discovered primordial black holes appealing as dark matter candidate because would be made of ordinary spacetime, just extremely warped, wouldn't require new particles or exotic physics, just same general relativity we already understand. Would be completely dark, emitting no light, would interact with other matter only through gravity exactly as dark matter appears to do, for while seemed promising possibility could explain dark matter without invoking particle physics beyond standard model. We found, however, multiple evidence lines now ruled out primordial black holes as dark matter primary component, at least for most mass ranges. Gravitational microlensing surveys searching for machos would have detected primordial black holes in certain mass ranges and didn't find enough. Cosmic microwave background observations constrain how many small primordial black holes could have formed. Ancient stars would have been disrupted by close black hole encounters, survived in larger numbers than expected if primordial black holes common. Each evidence piece closed off another possible primordial black hole mass range, leaving only narrow windows where might still account for dark matter. We learned beyond specific particle candidates, physicists also explored more radical possibilities. Some theories suggest dark matter might not be particles at all but rather modification to our gravity understanding itself. Most developed of these ideas, called MOND, modified Newtonian dynamics, proposed by physicist Mordechai Milgram 1983, suggests Newton's gravity law needs modification when gravitational accelerations become extremely weak as they are in galaxy outer regions. We discovered in MOND relationship between force and acceleration changes when accelerations fall below certain threshold, roughly 1/10 billionth of Earth's surface gravity. Below this threshold, gravitational effects become stronger than Newton's laws would predict, which could explain why stars in galaxy outer parts orbit faster than expected without needing to invoke dark matter. MOND had some successes. can explain galaxy rotation curves quite well with single adjustable parameter, predicted relationship between galaxy properties and rotation later observationally confirmed. We found, however, MOND faces significant challenges, struggles to explain galaxy cluster behavior like bullet cluster, where mass and ordinary matter separation seems to require actual dark matter rather than modified gravity. Doesn't naturally explain cosmic microwave background patterns fitting so well with dark matter models. MOND not complete gravity theory. Modifies Newtonian gravity but doesn't have fully developed relativistic version replacing Einstein's general relativity in all situations. Most physicists view MOND as interesting idea capturing something true about galaxy dynamics but ultimately doesn't provide complete dark matter alternative. We learned ongoing failure to directly detect dark matter particles, whether WIMPs or axions or anything else, led some physicists to wonder whether dark matter might be even more exotic than anyone imagined. Perhaps dark matter exists in dark sector, entire hidden particle and force realm mirroring our own but interacting with ordinary matter only through gravity. In this view might be dark photons, dark electrons, even dark atoms and dark chemistry, all invisible to us because don't couple to electromagnetic force allowing us to see things. We discovered in most elaborate versions of this idea could be dark stars, dark planets, perhaps even dark life, entire shadow universe coexisting with ours, overlapping in space but forever invisible because two realms interact only gravitationally. We would feel dark matter's gravity and it would feel ours but could never see it, touch it, or communicate with it in any conventional way. Highly speculative, of course. No direct evidence for such elaborate dark sectors, but idea illustrates how far physicists willing to go imagining what dark matter might be. Each fact a gentle step in understanding's branching. The gradual realization that dark matter could be many different things, axions or primordial black holes or modified gravity or entire dark sectors. From light-abundant axions to early universe black holes, from MOND's modified gravity to shadow universes of dark particles, all possibilities remain open. Rest in this vast uncertainty now. This recognition that we truly don't know what dark matter is. The universe holds perhaps its deepest secret still, revealing only that something invisible is there, waiting to be understood. Let yourself drift with these possibilities, these trillions of axions perhaps passing through you, these dark sector particles in their invisible realm, these alternative explanations, each as mysterious as the last, peaceful and unknown, carried gently towards sleep. As we continue our peaceful journey through the story of dark matter, we move from the many hypotheses about what dark matter might be to exploring how dark matter shapes the universe we see and how it influences the formation and evolution of galaxies. Dark matter is not just a passive component of the cosmos, it is the invisible architect that determines where and how galaxies form, the scaffolding upon which the visible universe is built. In the current understanding of cosmology, dark matter played an essential role in the formation of the first structures in the universe. In the very early universe, just after the Big Bang, both ordinary matter and dark matter were spread almost uniformly throughout space, with only the tiniest variations in density. Quantum fluctuations stretched to cosmic scales by the rapid expansion of inflation. But from these small seeds, all cosmic structure would eventually grow. The crucial difference between ordinary matter and dark matter in the early universe was that ordinary matter was hot and interacted with radiation. In the first 380,000 years after the Big Bang, before atoms formed, ordinary matter existed as a plasma of protons, electrons, and photons all interacting intensely with each other. The pressure from this radiation prevented the ordinary matter from collapsing under gravity. Whenever gravity tried to pull matter together, the radiation pressure pushed back, creating oscillations, sound waves traveling through the cosmic plasma. Dark matter, on the other hand, didn't interact with radiation at all. It felt only gravity, no pressure, no electromagnetic forces. This meant that dark matter could begin collapsing under its own gravity immediately, without waiting for the universe to cool down. As the dark matter clumped together, it created gravitational wells, regions of space where the gravitational pull was stronger. These gravitational wells became the seeds around which galaxies would eventually form. When the universe finally cooled enough for atoms to form, the event cosmologists call recombination, which occurred about 380,000 years after the Big Bang, the ordinary matter suddenly decoupled from radiation. The photons could now stream freely through space, becoming the cosmic microwave background we observe today. The ordinary matter, no longer supported by radiation pressure, began falling into the gravitational wells that dark matter had already created. It was as if dark matter had laid the foundation, and ordinary matter then moved in to build the visible structures. This process of structure formation continued over hundreds of millions of years. The dark matter halos grew larger through gravitational attraction, merging with other halos in a hierarchical process. Smaller halos combined to form larger ones, which combined to form larger ones still, building up the cosmic web we see today. Computer simulations of this process, starting from the tiny density fluctuations in the early universe and evolving forward in time using only gravity, produce structures that look remarkably like the distribution of galaxies we observe, but only if dark matter is included in the simulation. Within these dark matter halos, ordinary matter accumulated, drawn in by gravity. As the gas fell into the dark matter wells, it heated up from the compression and began to glow. In the densest regions, the gas became hot and dense enough for stars to form. The first stars in the universe, born perhaps 100 to 200 million years after the Big Bang, formed inside dark matter halos. These halos provided the gravitational anchor that allowed gas to collect and cool and eventually ignite nuclear fusion. Without dark matter, the first stars would have taken much longer to form, if they could have formed at all. This relationship between dark matter and galaxy formation means that the properties of galaxies are intimately connected to the properties of the dark matter halos they inhabit. The mass of a galaxy's dark matter halo largely determines how massive the galaxy itself can become, how many stars it can form, and how it evolves over time. Galaxies are not isolated islands of stars but rather the visible centers of much larger dark matter structures that extend far beyond the visible light. Observations of galaxy formation and evolution over cosmic time support this dark matter-driven picture. When astronomers look at distant galaxies, they're seeing them as they were billions of years ago because their light has taken that long to reach us. By studying galaxies at different distances, and therefore different times in cosmic history, astronomers can trace how galaxies have grown and changed. What they find matches the predictions of dark matter simulations. Galaxies were smaller and more irregular in the early universe, and they've grown larger and more structured through mergers and the continuous accretion of gas falling into their dark matter halos. The dark matter halo also affects how galaxies behave today. The rotation curves we discussed earlier, the observation that led Vera Rubin to conclude that galaxies contain dark matter, are a direct consequence of the dark matter halo's gravitational influence. Stars and gas orbit within the gravitational potential created by both the visible matter and the much more massive dark matter halo. The shape of the rotation curve tells astronomers about the distribution of dark matter, how concentrated it is toward the center versus how much extends into the outer regions. Different galaxy types have different dark matter halo properties. Dwarf galaxies, small galaxies containing only millions to billions of stars rather than hundreds of billions, appear to be dominated by dark matter even more than large galaxies like the Milky Way. In some dwarf galaxies, dark matter may outweigh ordinary matter by as much as 100 to 1 or even more. These small galaxies are essentially dark matter halos with just a tiny amount of visible matter at the center, making them excellent laboratories for studying dark matter's properties. One of the puzzling aspects of galaxy formation that connects to dark matter is the question of galaxy diversity. Simulations of dark matter predict that there should be a smooth distribution of halo masses, from tiny halos to enormous ones. Yet when astronomers look at actual galaxies, they find that not every dark matter halo of a given size contains the same amount of stars and gas. Some halos appear to be very efficient at forming stars, converting a large fraction of their gas into stars, while others seem to be much less efficient, forming far fewer stars than they could given the amount of gas available. Understanding why some halos form more stars than others involves complicated astrophysics, the feedback from supernova explosions, the radiation from young stars, the gas flows into and out of galaxies, the influence of supermassive black holes at galaxy centers. All these processes can heat gas and blow it out of galaxies, suppressing star formation. But the underlying framework is still provided by dark matter. The dark matter halo determines the basic gravitational environment, and then the complex interplay of astrophysical processes determines what happens to the ordinary matter within that environment. Another area where dark matter's influence appears is in gravitational lensing on smaller scales. We've mentioned gravitational lensing by galaxy clusters, the bending of light from distant galaxies by the cluster's gravity, but lensing happens at all scales where there's significant mass. Individual galaxies can act as lenses, and by studying how they bend light from background objects, astronomers can map the distribution of dark matter in those galaxies with great precision. Some of the most detailed dark matter maps come from a phenomenon called strong gravitational lensing, where a foreground galaxy's gravity is so strong that it creates multiple images of a background galaxy, or stretches it into arcs and rings, dramatic distortions visible in deep telescope images. By modeling these lensing effects, astronomers can reconstruct the distribution of all the mass in the foreground galaxy, including the dark matter. These studies consistently show that galaxies are surrounded by extended dark matter halos, with the dark matter following a particular distribution, denser toward the center, more diffuse in the outer regions. And so we learned in current cosmology understanding dark matter played a central role in first universe structures formation. In very early universe just after Big Bang, both ordinary matter and dark matter spread almost uniformly throughout space with only tiniest density variations. Quantum fluctuations stretched to cosmic scales by rapid inflation expansion. From these small seeds all cosmic structure would eventually grow. We discovered crucial difference between ordinary matter and dark matter in early universe was ordinary matter was hot and interacted with radiation. In first 380,000 years after Big Bang before atoms formed, ordinary matter existed as protons, electrons, photons, plasma, all intensely interacting. Radiation pressure prevented ordinary matter from collapsing under gravity. Whenever gravity tried pulling matter together, radiation pressure pushed back, creating oscillations, sound waves traveling through cosmic plasma. We found dark matter, on the other hand, didn't interact with radiation at all, felt only gravity, no pressure, no electromagnetic forces. Meant dark matter could begin collapsing under own gravity immediately without waiting for universe to cool down. As dark matter clumped together, created gravitational wells, space regions where gravitational pull was stronger. These gravitational wells became seeds around which galaxies would eventually form. We learned when universe finally cooled enough for atoms to form, event cosmologists call recombination, occurring about 380,000 years after Big Bang. Ordinary matter suddenly decoupled from radiation. Photons could now stream freely through space, becoming cosmic microwave background we observe today. Ordinary matter, no longer supported by radiation pressure, began falling into gravitational wells dark matter had already created, as if dark matter laid foundation and ordinary matter then moved in to build visible structures. We discovered structure formation process continued over hundreds of millions of years. Dark matter halos grew larger through gravitational attraction merging with other halos in hierarchical process. Smaller halos combined forming larger ones, which combined forming larger ones, still building up cosmic web we see today. Computer simulations of this process, starting from tiny early universe density fluctuations and evolving forward in time using only gravity, produce structures looking remarkably like observed galaxy distribution, but only if dark matter included in simulation. We found within these dark matter halos ordinary matter accumulated, drawn in by gravity, as gas fell into dark matter wells, heated up from compression and began to glow. In densest regions, gas became hot and dense enough for stars to form. First universe stars, born perhaps 100 to 200 million years after Big Bang, formed inside dark matter halos. Halos provided gravitational anchor, allowing gas to collect and cool and eventually ignite nuclear fusion. Without dark matter, first stars would have taken much longer to form, if could have formed at all. We learned this relationship between dark matter and galaxy formation means galaxy properties intimately connected to dark matter halo properties they inhabit. Galaxies' dark matter halo mass largely determines how massive galaxy itself can become, how many stars can form, how evolves over time. Galaxies, not isolated star islands but visible centers of much larger dark matter structures extending far beyond visible light. We discovered galaxy formation and evolution observations over cosmic time support this dark matter-driven picture. When astronomers look at distant galaxies, seeing them as they were billions of years ago, light took that long to reach us. By studying galaxies at different distances, therefore different cosmic history times, astronomers trace how galaxies grown and changed. Findings match dark matter simulation predictions. Galaxies were smaller and more irregular in early universe, grown larger and more structured through mergers and continuous gas accretion falling into dark matter halos. We found dark matter halo also affects how galaxies behave today. Rotation curves, observation leading Vera Rubin to conclude galaxies contain dark matter. are direct consequence of dark matter halo gravitational influence. Stars and gas orbit within gravitational potential created by both visible matter and much more massive dark matter halo. Rotation curve shape tells astronomers about dark matter distribution, how concentrated towards center versus how much extends into outer regions. We learned different galaxy types have different dark matter halo properties. Dwarf galaxies, small galaxies containing only millions to billions of stars rather than hundreds of billions, appear dominated by dark matter even more than large galaxies like Milky Way. In some dwarf galaxies, dark matter may outweigh ordinary matter by as much as 100 to 1 or more. Small galaxies, essentially dark matter halos with just tiny visible matter amount at center, making them excellent dark matter properties study laboratories. We discovered one puzzling galaxy formation aspect connecting to dark matter is galaxy diversity question. Dark matter simulations predict there should be smooth halo mass distribution from tiny halos to enormous ones. Yet when astronomers look at actual galaxies, find not every dark matter halo of given size contains same star and gas amount. Some halos appear very efficient at forming stars, converting large gas fraction into stars, while others much less efficient, forming far fewer stars than could give an available gas amount. We found understanding why some halos form more stars than others involves complicated astrophysics, feedback from supernova explosions, young star radiation, gas flows into and out of galaxies, supermassive black hole influence at galaxy centers. All these processes can heat gas and blow it out of galaxies, suppressing star formation, but underlying framework still provided by dark matter. Dark matter halo determines basic gravitational environment, then complex astrophysical process interplay determines what happens to ordinary matter within that environment. We learned another area where dark matter's influence appears is in gravitational lensing on smaller scales. Mentioned gravitational lensing by galaxy clusters, light bending from distant galaxies by clusters' gravity, but lensing happens at all scales where there's significant mass. Individual galaxies can act as lenses. By studying how they bend light from background objects, astronomers can map dark matter distribution in those galaxies with great precision. We discovered some most detailed dark matter maps come from phenomenon called strong gravitational lensing, where foreground galaxy gravity so strong creates multiple background galaxy images or stretches it into arcs and rings. Dramatic distortions visible in deep telescope images. By modeling these lensing effects, astronomers can reconstruct all foreground galaxy mass distribution, including dark matter. Studies consistently show galaxies surrounded by extended dark matter halos, with dark matter following particular distribution, denser toward center, more diffuse in outer regions. Each fact a gentle step in understanding's deepening, the gradual realization that dark matter is not passive but active, the architect of structure, the foundation for galaxy formation, the invisible framework holding everything together. From early universe gravitational wells to first star formation, from hierarchical halo growth to galaxy diversity puzzles, from dwarf galaxy dark matter dominance to strong lensing maps, all revealing dark matter's central role. Rest in this architectural understanding now, this recognition that dark matter built the universe we see. Every galaxy formed in a dark matter halo. Every star owes its existence to dark matter's gravitational pull gathering gas together. Let yourself drift with this cosmic construction, these dark matter halos merging and growing over billions of years, building the scaffolding for galaxies to form, invisible architects working patiently through gravity alone. carried gently towards sleep. As we approach the end of our peaceful journey through the story of dark matter, we turn to the frontiers of current research and the profound questions that remain. Despite decades of study, dark matter keeps its secrets well, but each year brings new observations, new experiments, and new insights that bring us closer to understanding this mysterious substance that makes up most of the matter in the universe. The search continues, patient and determined. One of the most exciting recent developments in dark matter research involves using artificial intelligence and machine learning to analyze the vast amounts of data coming from telescopes and detectors. Modern astronomical surveys capture images of billions of galaxies, and analyzing all this data by hand would be impossible. Machine learning algorithms can be trained to identify the subtle signs of gravitational lensing, the slight distortions in galaxy shapes caused by dark matter between us and them, automatically detecting patterns that would take humans years to find. These AI-powered analyses have created detailed maps of dark matter distribution across large regions of the universe. Surveys like the Dark Energy Survey and the upcoming Legacy Survey of Space and Time will map dark matter over billions of light years, revealing the cosmic web in unprecedented detail. By comparing these maps to simulations, researchers can test their theories about dark matter's properties, how it clumps, how it interacts with itself, if at all, and how it influenced the evolution of cosmic structure over billions of years. Another promising avenue of research involves indirect detection of dark matter through its potential annihilation or decay. If dark matter particles can collide with each other and annihilate, converting their mass into energy in the form of other particles, as matter and antimatter do, then regions with high dark matter density might produce detectable signals. The centers of galaxies, including our own Milky Way, should have particularly high dark matter concentrations, making them good places to look for annihilation signals. Astronomers using gamma-ray telescopes have searched for excess gamma radiation coming from the galactic center or from dwarf galaxies orbiting the Milky Way. Dwarf galaxies are particularly interesting targets because they're dominated by dark matter with relatively little ordinary matter to create confusing background signals. Several studies have reported hints of possible excess gamma rays that could be explained by dark matter annihilation, but these signals remain controversial. Alternative explanations involving ordinary astrophysical processes, pulsars, supernova remnants, cosmic rays, can't yet be ruled out. The search for dark matter has also expanded beyond our galaxy. Some researchers are looking for dark matter effects in the cosmic microwave background at even finer scales than previously examined. During the epoch of recombination, when the cosmic microwave background was created, dark matter would have been clumping under gravity. These clumps could have left tiny imprints on the radiation, subtle variations in temperature and polarization at small angular scales. New experiments with greater sensitivity are searching for these signatures, which could reveal properties of dark matter that other methods can't access. Another intriguing possibility involves primordial gravitational waves, ripples in spacetime produced in the very early universe. Certain dark matter scenarios, particularly those involving phase transitions in a dark sector in the early universe, would have produced gravitational waves with specific characteristics. Detectors like LIGO, which discovered gravitational waves from merging black holes and neutron stars, and future space-based detectors like LISA, might be able to detect these primordial signals. If found, they could provide a completely independent window into dark matter's nature and its role in the early universe. The mystery of dark matter has also inspired theoretical physicists to reconsider fundamental assumptions about the nature of space and time. Some approaches to quantum gravity, the still undeveloped theory that would unite quantum mechanics and general relativity, suggest that spacetime itself might be emergent, arising from more fundamental quantum information. In these frameworks, what we perceive as dark matter might be a manifestation of how gravity emerges from quantum entanglement, rather than being an actual substance at all. These ideas are highly speculative and difficult to test, but they illustrate how the dark matter puzzle connects to the deepest questions in physics. Despite all the searches and all the observations, we still don't know what dark matter is. This might seem like a failure, but it's actually a tremendous opportunity. We know dark matter exists. The evidence is overwhelming and comes from multiple independent sources. We know approximately how much of it there is and how it's distributed. We know it doesn't emit, absorb, or reflect light, and that it interacts very weakly if at all with ordinary matter except through gravity. These constraints are powerful, ruling out many possibilities and guiding future searches. The null results from direct detection experiments, rather than being disappointing, are actually telling us something important. They're saying that if dark matter is made of particles, those particles are even more elusive than we thought, more weakly interacting, or heavier, or lighter than our initial guesses. Each experiment that finds nothing narrows the range of possibilities, making the remaining parameter space smaller and more defined. We're closing in on the answer, even if we haven't found it yet. One thing that makes the dark matter mystery so compelling is that its solution will likely bring unexpected surprises. History shows that when we discover something truly new about nature, it opens doors we didn't know existed. The discovery of the electron led to quantum mechanics and the entire electronics revolution. The discovery of nuclear energy led to our understanding of how stars shine and where elements come from. When we finally identify dark matter, it will almost certainly reveal new physics, new particles, new forces, or new aspects of gravity that we can't currently imagine. Some physicists wonder whether the dark matter problem might be solved by a young researcher currently in school, or by someone who hasn't even been born yet. Science builds across generations, with each era contributing pieces to the puzzle. The astronomers who first noticed that galaxy rotation curves were flat didn't have the theoretical framework or the technology to understand what they were seeing. But their careful observations laid the groundwork for later generations to build upon. Perhaps today's observations and experiments are laying similar groundwork for future breakthroughs we can't yet envision. And so our journey through dark matter comes to its end, though the search for understanding continues. We've traveled from Fritz Zwicky's 1933 observations of galaxy clusters moving too fast, through Vera Rubin's rotation curves showing stars orbiting faster than visible matter could explain, to the realization that the universe is 27% dark matter, 5 times more than all the ordinary matter we can see. We've learned that dark matter can't be ordinary atoms. Big Bang nucleosynthesis proved there isn't enough ordinary matter. That searches for machos through gravitational microlensing found only a small fraction of the needed mass. That WIMPs, despite decades of searching in underground detectors, have not yet been definitively detected. That axions remain a possibility, with experiments patiently searching for their whisper-quiet signals. that primordial black holes are ruled out for most mass ranges. That MOND, while interesting, can't explain all the observations. We've discovered the overwhelming evidence for dark matter's existence, the bullet cluster showing separated mass and ordinary matter, the cosmic web structure that couldn't have formed without dark matter, the cosmic microwave background patterns revealing the universe's composition with precision. We've understood how dark matter created the gravitational wells in the early universe that allowed the first stars and galaxies to form, how it provides the scaffolding for all cosmic structure, how every galaxy sits at the center of a vast dark matter halo extending far beyond the visible light. We've explored exotic possibilities, dark sectors with their own particles and forces, entire shadow universes overlapping with ours. We've seen how machine learning maps dark matter across the cosmos, how gamma-ray telescopes search for annihilation signals, how gravitational wave detectors might reveal dark matter's primordial imprint. We've recognized that every null result tells us something, narrowing the possibilities, guiding future searches. As you rest now, know that you've journeyed through one of science's greatest mysteries. Dark matter surrounds you right now, permeates this room, this planet, the solar system, the galaxy. You're floating in an invisible ocean of dark matter, just as Earth orbits the Sun through dark matter, just as the Sun orbits the galactic center carrying its dark matter halo along. Dark matter was here before the stars formed and will be here long after they die. It is the majority of the matter universe, yet it remains hidden from all our senses except gravity's pull. This is both humbling and awe-inspiring. Most of reality is invisible to us. We are made of the minority component of matter, the ordinary atoms that emit and absorb light, that clump together to form stars and planets and people. We are, in a sense, the rare exception, the unusual matter that shines and reflects and creates chemistry and complexity. Dark matter is the rule, the foundation, the invisible majority that makes galaxies possible and holds the universe together. There's a profound mystery in this. We live in a universe we can see only a small fraction of, made mostly of something we cannot directly detect. Yet we know it's there, can map its distribution, can trace its influence through billions of years of cosmic history. Gravity alone reveals dark matter, that universal attraction between all matter, connecting the visible to the invisible. Perhaps someday, maybe soon, maybe generations from now, we'll understand what dark matter truly is. Perhaps we'll detect the particle, or discover the modification to gravity, or uncover the hidden sector. Perhaps the answer will be something no one has yet imagined, opening new realms of physics as revolutionary as quantum mechanics or relativity. Or perhaps dark matter will keep its secrets even longer, remaining mysterious and elusive, reminding us that the universe is under no obligation to reveal itself to us easily. But the search itself is beautiful. Scientists around the world, across generations, working together to solve the mystery, building detectors deep underground, launching satellites, developing theories, analyzing data. Each experiment, each observation, each calculation adding a small piece to the vast puzzle. This is science at its best, patient, creative, humble in the face of the unknown, persistent in seeking understanding. As you drift towards sleep now, let yourself feel the dark matter around you, invisible and unknowable yet real. Let yourself be part of this cosmic mystery, this universe mostly made of something hidden. The dark matter that holds galaxies together holds you too, It's gravity contributing to the gravitational field you feel as weight, connecting you to the cosmos in ways both seen and unseen. Rest in the mystery. Sleep in the invisible universe. Know that most of what exists is dark, is hidden, is waiting to be understood. And that's okay. That's beautiful. The universe keeps its deepest secrets, and we keep searching, keep wondering, keep reaching toward understanding. Good night, surrounded by dark matter. Good night, floating in the invisible ocean. Good night, child of the universe's rare shining minority, made of atoms that can wonder about the dark majority that surrounds them. Sleep well. The dark matter remains, patient and eternal, holding everything together.